Good afternoon and welcome everyone. My name is Ákos Rechtorisz. I'm the product manager at StruSoft, responsible for developing FEM-Design connectivity with other software solutions. In today's webinar, I will guide you through the main connection possibilities between Revit and FEM-Design. The focus is on practical workflows, how data moves between Revit and FEM-Design, what we can transfer, and which workflow to use in different situations. There are two main ways to connect Revit and FEM-Design. One is the IFC workflow, where we exchange the physical model through IFC. The other is the direct add-in workflow. It uses the StruSoft Revit add-in and exchanges data through XML, our own data exchange format. Both workflows can go in either direction, from Revit to FEM-Design and back again. But they are not used for the same purpose. The key question is, which connection should be used and when? Let's start with a short overview. IFC is an internationally developed and ISO standardized open data format. It is the most widely used BIM exchange format, and it is supported by hundreds of applications worldwide. Several IFC versions are available, and both Revit and FEM-Design support them. But for Revit-based workflows, IFC 2x3 coordination view is still often the safest and most predictable starting point. That is why I usually recommend starting with IFC 2x3. The second workflow is the add-in based connection. It's existed for many years, but after Revit 2023, it had to be redesigned because Autodesk changed the analytical model concept in Revit. Today, I will focus on the current second-generation add-in workflow. Its latest release can be downloaded free of charge from the FEM-Design wiki. It supports Revit 2026 and 27, and it was published yesterday, so it is very fresh, almost hot. After installation, it appears directly inside the Revit user interface. So what is the main task? In structural design, we need an analytical model suitable for calculation. In the IFC workflow, the physical model comes from Revit into FEM-Design. During import, FEM-Design creates the analytical model from the physical geometry. The engineer then checks, corrects, and completes it. In the add-in workflow, the analytical model is already created in Revit. It can include analytical members, panels, basic supports, and simple loads. Then it is transferred to FEM-Design through XML. So in simple terms, IFC starts mainly from a physical model. The add-in starts mainly from an analytical model. Let's now look first at the direct Revit connection using the add-in. We start with a physical model in Revit. This can be an architecture model or a structural model. From this physical model, we can generate an analytical model directly inside Revit project. After that, the StruSoft add-in can export this analytical model to FEM-Design. The goal of the add-in workflow is to transfer all relevant structural design data without data loss. It is important to understand that in Revit, not every physical structural object has a native analytical counterpart. Isolated and slab foundations are good examples. They don't have an analytical representation in Revit, while FEM-Design has object types for them. Since these are still important structural objects, the add-in can transfer them to FEM-Design as part of the exchange workflow. The same is true for levels and grids. They are not analytical elements, but they are useful reference objects for positioning, orientation, view definition, and identification. Therefore, the add-in transfers them as well. In the current Revit concept, analytical objects are independent from physical objects. They are not automatically linked to them, and they don't follow every change in the physical model. The advantage is that we have more flexibility when building the analytical model. In fact, analytical objects can even exist without physical counterparts. This was an important change in Revit 2023. Before that, analytical counterparts were always directly linked to the physical structural objects. So, if you want to create analytical objects from physical load-bearing elements, we first have to prepare the Revit model properly. For walls, the structural parameter has to be activated. The same applies to floors. For columns, Revit already has a dedicated structural column tool, so you don't need to set anything else. For beams and bars, the structural framing tool is used. Structural foundations are a special case. They don't have native Revit analytical counterparts, but if we want, they can still be exported to FEM-Design by the add-in. After this preparation, we can use Revit's analytical automation tools to generate the analytical model. This can be fully automatic, but it can also be controlled by settings. With automation customization, we can define how analytical elements should adjust to each other, in what order, with what priority, and within what tolerance. Revit also allows manual analytical modeling. We can create analytical members and panels directly from the Analyze tab. When analytical elements are generated from physical objects, they usually inherit material and section information. But manually created analytical elements may not have all required data. This is not a problem because during export, we can assign missing materials, sections, or panel thicknesses. For example, if a member has no section, we can define a default starting section by material type. If a panel has 0 thickness, we can define a substitute thickness for FEM-Design. Inside Revit, we can also define boundary conditions and analytical links. Boundary conditions correspond to supports in FEM-Design. Links correspond to FEM-Design's point-to-point connections. Revit can also define simple loads, point loads, line loads, and area loads, organized into load cases. Levels and grids can also be included, as mentioned before. Levels may represent building stories, but they can also be general horizontal reference plans. Grids are useful for orientation and later model checking. To export the model, we start the StruSoft add-in command, export StruXML. The export is guided by a sequence of dialogues. First, we define which object should be exported. We can export all relevant objects in project or only a current selection. This is useful if we want to export only one story, one part of the model, or only selected element types. Later, several StruXML files can be imported or merged into one FEM-Design project. We then select the design code. This is important because the material and section databases used in the next steps depend on the selected standard. Then we arrive at position settings. In many BIM projects, especially large public or infrastructure-related projects, the model is placed in real-world coordinates. This is important for coordination and model federation. However, structural engineers usually prefer to work close to the origin and aligned with the global axis of the analysis software. Therefore, the add-in can move and rotate the model automatically during export. This means that the model located far from the Revit origin can be exported to FEM-Design in a more convenient analysis position. This is also important for bidirectional communication. If the model later comes back from FEM-Design to Revit, it has to return to its original Revit position. The add-in can handle this automatically because the transformation values are stored in the Revit project itself. Revit also has different reference systems: global origin, project base point, and survey point. During export, we can choose which reference system should be used. The next step is type mapping. Here we decide how Revit elements should be transferred to FEM-Design. For example, an analytical member with a beam role can become a FEM-Design beam, a truss, or only a 3D reference line. In the list, we can see analytical members and panels, but also grids, levels, boundary conditions, structural foundations, and loads. After type mapping, we map Revit materials to FEM-Design materials. We can use automatic default mapping based on material types, or we can manually select the exact FEM-Design material from the database. To find the required material quickly, we can simply type part of its name in the search field. Then we map the cross-sections of analytical members. A useful feature is that the add-in can create new FEM-Design sections from Revit data. With the Create New option, the section geometry is saved into StruXML file. During import, FEM-Design assigns the new section to the corresponding analytical members. Material and section mapping can also be based on custom StruXML libraries, not only on the standard built-in FEM-Design databases. At the end of the export, we receive a report. This summarizes the result and lists possible warnings, for example, missing material or section mappings. Now we can open the exported StruXML file in FEM-Design. Usually, we open it in the 3D structure module, but it can also be opened in the plate module, for example, if we transfer only one floor system with its supporting elements. The file can be opened with the open command or inserted with the paste command. Paste is useful when we build up one FEM-Design project from several StruXML files. A single file can also be opened simple by drag and drop. The import itself is very fast. After import, the design code follows the standard selected in the add-in export settings. We can now see the analytical members and panels together with levels and grids. If we switch on the physical representation, we can also see the assigned thicknesses and cross-sections. The filter panel in FEM-Design helps us navigate the imported model. Elements can be grouped by story, by axis, by type, by support type, by original Revit identifier or name, by material, or by section, including the new sections generated from Revit section data, like this selected example. Element information can also be displayed as labels in the model space, or checked by hovering over the elements. This is useful both for model checking and for documentation. Supports are imported according to the boundary conditions defined in Revit. Loads are also imported together with the load cases. However, additional loads, design load groups, and combinations have to be completed inside FEM-Design. After import, even if the model looks correct, we should always check it. First, we should look for small geometry problems and connection issues. These can appear even in well-prepared Revit models due to the modeling tolerances or coordinate handling. FEM-Design provides the correct model function to find and fix them. It can find short elements, inaccurate line elements, small regions, or other problematic objects, and it can correct them under user control. After correction, it is useful to run the check again. The goal is that the number of problematic objects should go down and finally converge close to the zero. Another useful check is finite element mesh generation. If the mesh is generated quickly, without unnecessary refinements or error messages, this means that the geometry is correct. We can also run a simple analysis, for example, with automatic self-weight, and check the displacement shape. This is a very practical quality check. If elements are not connected properly, or if supports are missing, the problem usually becomes visible very quickly. In this example, the displacement animation shows that some walls were not supported in Revit. and the left side of the frame is weakly supported. Inside FEM-Design, with the modeling tools, we can add the missing supports or propose a more stable bracing or support system. After that, we can continue with the normal analysis and design workflow. For example, we can design steel members and optimize their cross-sections based on their utilization. After the model has been checked and designed, it can also be sent back to Revit. Now let's look at the add-in workflow in the other direction, from FEM-Design to Revit. First, we export the FEM-Design model to StruXML. Then, inside Revit, we use the import function of the StruSoft add-in. Again, the purpose is to transfer all relevant information without data loss. The first step is file selection. Here we can also decide whether to import the original FEM-Design data as reference information together with the unique element identifiers. Then we define type mapping and filtering. We can decide which elements should be imported and which should be skipped. For example, if stories and axes already exist in the host Revit project, we can leave them out. Some FEM-Design objects become physical Revit objects. For example, a slab foundation can become a Revit slab foundation, because Revit doesn't have a corresponding analytical object for it, as mentioned before. Then we do the material and section mapping. For each item, we can select an existing Revit material or section, or choose Create New. This is one of the strongest features of this workflow. The add-in can create new Revit materials and section types from the FEM-Design data stored in the StruXML file. So the final design materials and sections can be used directly inside Revit. There is no need to recreate them manually in the family editor, either before or after import. At the end, we again receive an import report. Just for demonstration, I show a simple warning here. One column has no section mapping. The element is still imported without a section assignment. If we select an imported element in Revit, we can see additional data coming from FEM-Design. This may include the global unique ID, name, material, profile, and object type. At the same time, the analytical member receives the corresponding structural material, role, and section type. From this analytical information, we can create the final physical Revit element using Revit's automatic converter tool. So after import, it is very simple step. We select the full imported analytical structure and Revit converts it into the required physical elements. Now, a few words about change management. In Revit, there is no dedicated change management tool, but we can use linked models for visual comparison. For example, a new StruXML version can be imported into a separate Revit file and then linked into the previous Revit project. With different colors, we can compare the old and new status visually. In Revit, the same reference model idea can also be used with IFC and CAD files. On the FEM-Design side, we can compare different StruXML files directly with the Compare Files tool. This tool shows new, deleted, and modified elements with color visualization and detailed lists of changes in geometry and properties. Now I would like to show a few additional workflow highlights related to the add-in connection. The first one is Impact Precast. Impact is another StruSoft product integrated into Revit. It supports modeling, detailing, shop drawings, and manufacturing workflows for precast projects. Because Impact works inside Revit, it creates native Revit objects. This means that the analytical counterparts of Impact Precast elements can be transferred to FEM-Design through the add-in. There are a few details to keep in mind. Impact creates precast panels in Revit as profile beam or column objects. To transfer them to FEM-Design, we first convert them into analytical members using Revit's analytical automation. Since the conversion uses the original panel geometry, the part's visibility should be set to show original. Inside FEM-Design, these transferred elements may arrive as profile beams and columns. If we want to analyze them as precast panels, shell objects, we can convert them quickly with the convert function. So thanks to the add-in, we also solved the connection between impact and FEM-Design. The reverse workflow is also supported. Profile panel shell objects modeled in FEM-Design, such as hollow core slabs or walls, can be imported into Revit as profiled analytical members, reference contour lines, or just simplified physical panel objects. Another special case is foundations and pies. If foundation objects arrive in FEM-Design, we can decide whether we want to use them as structural objects or only as references. They can also be converted into drawing solid reference objects, or with a two-step workflow, they can be converted into pies. First, we define a soil object. Then, we use the convert function to create pies with spring data generated automatically from the soil connection. These pies can also be sent back to Revit. Since Revit doesn't have a dedicated pile object, they can be represented as profiled analytical members or as reference model lines. Point and slab foundations designed in FEM-Design can be also transferred as physical Revit foundation objects. Wall foundations can be represented as profiled analytical members and later converted into beams. Another recent improvement and new feature is that FEM-Design column and wall corbels can also be transferred to Revit as profiled analytical members and panels. Inside Revit, the automatic converter can then create the corresponding physical objects from these analytical elements. Now, let's move to the IFC-based connection and start with the Revit to FEM-Design direction. Here, the goal is to extract all information needed for structural design from a physical architectural or structural model and use it to create a calculation-ready analytical model in FEM-Design. Again, we want to avoid data loss. But in this workflow, it is important to define what data loss actually means. For beam coordination tools, data loss often means that every object should arrive exactly as it was modeled. For analysis software, the goal is different. We need the load-bearing structural elements, their relevant properties, and the reference objects that are useful for design. For example, we don't need the detailed geometry of windows and doors, but we need the openings in the load-bearing walls and slabs. We may also need non-structural reference objects, such as stairs, canopies, curtain walls, or large mechanical objects, if they help us define loads. With IFC, the main task is to convert the physical model into an analytical model inside FEM-Design. This workflow has two main parts. First, during import, we filter object types, remove unnecessary objects, map data, and convert physical objects into analytical elements. Second, after import, we adjust, connect, support, and check the analytical model to ensure continuous load transfer. What kind of problems can appear after importing a physical model? There can be small modeling issues, very short elements, duplicated objects, overlapping geometry, small openings, unnecessary points, or very sharp angles. All of these can affect the quality or success of finite element mesh generation. There can also be connection issues. Physical objects may touch each other correctly in architectural models, but the analytical lines and surfaces generated from their central lines and mid-surfaces will not automatically connect. This is why model correction and adjustment are essential in the IFC workflow. FEM-Design provides several tools for this. Filtering during import, correct model for geometry problems, adjust analytical model for element connections, and mesh check for verifying the finite element model. Before exporting from Revit, the sender should check a few things. The model may contain levels, grids, and rooms. As mentioned earlier, levels and grids are useful for positioning and coordination. Rooms can be useful as references for live load definition. There is an important Revit-specific rule. In Revit, only levels marked as building story are exported to IFC. Since grids and rooms are assigned to levels, they can also be exported only if the related level is a building story. Layer filtering is also important in IFC workflows. Revit doesn't use native layers inside the project, but it can still provide layer information in the IFC export. For this, Revit uses the layer settings defined for DWG or DXF export. So, if we want to control the IFC layer names, we have to modify them there. After the model is prepared, we set up the IFC export. For this workflow, as mentioned earlier, I recommend starting with the well-established IFC 2x3 Coordination View 2.0 setup. To customize its settings, we first duplicate the setup and save it under a new name. Then we check a few important export options. Revit categories should be mapped to the right IFC classes. For example, structural columns should be exported as IFC column. IFC also uses predefined types. These provide more detailed classification. For example, slabs can be classified as floors, roofs, stair landings, or base slabs. If the Revit project contains linked models, we can include them in the export if they contain elements needed for analysis. We can also decide whether to export only the visible elements of the current view or the whole project. If room locations and functions are needed later for defining loads, room export has to be activated. The default property set settings are usually enough for analysis workflow. For advanced settings, I recommend leaving all objects unselected. We don't need any further data for analysis. Finally, we can choose the coordinate base of the element coordinates, such as the internal origin or the survey point, similarly to the add-in workflow. After exporting the IFC file, we open it in FEM-Design. The following import steps are not Revit specific. They can also be used for IFC files from other modeling software, like Tekla, Archicad, or Allplan. First, we can filter the model by project hierarchy. If the IFC file contains several buildings or stories, we can import only the parts we need. FEM-Design can handle more than one building inside the project. Then we define positioning. To avoid issues with models located far from the origin, FEM-Design can move the model close to the origin and rotate it to the global axis. The transformation is stored, so the original position and orientation can be restored later during export. The next step is layer filtering. Here we can see the layer names coming from Revit. For example, the S-cores layer hosts the structural columns. Only elements on the selected layers will be imported. After that, we perform type filtering and mapping. Here we define how IFC object classes should be generated in FEM-Design. For example, IFC member objects can become editable analytical elements, such as beams or trusses, or reference objects, such as drawing solids or boundary regions. Some FEM-Design object types can generate related objects during import. For example, an IFC footing imported as a slab foundation can automatically receive the corresponding surface support tube. Some objects can be imported only as reference objects, such as stairs, spaces representing Revit rooms, or mechanical equipment that may represent significant loads. Next, we can apply geometry filtering. Very small members, plates, or openings can be removed based on size limits. We can also import the original physical geometry as reference solids. This helps us compare the original model with the generated analytical model. Then we perform material and cross-section mapping. As in the add-in workflow, FEM-Design can also generate new cross-sections if they don't exist in the database. This means that a Revit section with its specific geometry, like this hollow steel column section, can be created and stored in the FEM-Design section library. All these import settings, including mappings, can be saved. This is very useful in repeated project workflows. If new materials or sections appear later, only those new items need to be mapped. After import, FEM-Design shows a report. It may include warnings, for example, about geometry simplification. Similarly to StruXML workflow, we can import IFC files with open or paste. Open is useful for processing the full file in one step. Paste gives more control when we import by story, by layer, by element type, or from several IFC files. After import, the selected objects appear in FEM-Design. The result is color-coded. Green means that an object was created with its original geometry. Orange means that geometry modifications were applied during import. For example, the corner of these two walls was simplified during import to create a correct connection between the analytical wall panels. Blue means that we imported an object as a reference object on purpose. In this example, reference objects include stairs, mechanical equipment, foundations, and rooms. These help us define loads or understand the model context. For example, room labels, here you see office, can help us choose the right live load. The structural elements are imported as analytical elements according to their type. For example, columns can be imported with map, steel material, and section. After IFC import, the key engineering task is to connect the generated analytical elements. Let's look at a few examples. For walls and slabs, the initial state is usually not fully connected because the analytical surfaces are generated from the physical mid-surfaces. FEM-Design provides dedicated tools in Adjust Analytical Model. Shells can be adjusted to each other, extended or trimmed to any selected object, and aligned into common planes. For example, the bottommost option can align walls to the lowest wall plane. These options work within a user-defined tolerance. Bars can be adjusted in a similar way. They can be moved, extended, or trimmed to connect correctly at the intended nodes. In addition, we can use standard modeling commands to modify bars and shells, such as offset, stretch, split, trim, and extend, as well as region operation for shell elements. Stories, grids, and reference plans can also be used as adjustment targets. This is useful for trusses and frame structures, where nodes should connect to the 3D grid intersections automatically detected from the reference system. Let's look at a simple model corner example, where the correct model function automatically aligns and stretches the objects to the axis system in one quick step. When the model looks ready, we should check it by generating the finite element mesh. If the automatic mesh generation runs without errors, the analytical model is usually usable. If there are connection problems, FEM-Design will find them and show their location. In this example, the full mesh generation takes only about 2 seconds. But if we slow it down, we can see 6 steps behind it. Overlap checking, surface mesh generation, local refinement, mesh optimization, smoothing, and final geometry and topology checking. The important thing is to use the right correction tools at the right time and in the right order. For different structures, it is useful to have a clear workflow. And don't wait until the end to check the full model. It is much safer to check smaller model parts several times during the workflow. Tolerance settings are also very important. For example, with a 30 cm tolerance, FEM-Design may remove only the small unwanted openings and narrow regions. But with 40 cm, larger openings and hanging regions may also be affected. So tolerances should always match the purpose of the correction, and the results should be checked visually. Now let's briefly look at IFC export from FEM-Design to Revit. The FEM-Design's IFC exporter allows us to share all designed structural objects and details with other applications, including Revit. If a FEM-Design project contains several models, we can export only one selected model. We can also define a user coordinate system and export relative to that system. Elements can be exported with the current display colors. This is useful if we use color schemes in FEM-Design. For example, to show different wall thicknesses or steel sections or materials and so on. The Revit user can then immediately see the same visual difference. Objects with complex geometry may arrive in Revit as in-place elements. These are usually edited with the family editor. Simpler objects can be edited directly in place. For example, in Revit, we can modify the height, width, and thickness of a wall. The design parameters coming from FEM-Design are also available in Revit. This makes the design properties easier to follow and check inside the Revit projects. For example, the type mapping, the material mapping, or section mapping. Reinforcement designed in FEM-Design can also be exported as a 3D model. In Revit, these objects can be used as reference geometry while the design data remains available. This helps the Revit user create detailed reinforcement for shop drawing. The same applies to steel connections. FEM-Design can export design connection objects through IFC. Some parts, such as end plates or stiffeners, may be editable. Others, such as bolts, may be reference objects. But the important design data is still available. Type, material, dimensions, spacing, and connection identifiers. To summarize the webinar, the best connection between Revit and FEM-Design depends on the model we receive. If the model is analytical and prepared in Revit, the add-in and StruXML workflow is usually the fastest and most direct option. If the model is a physical, architectural, or structural model, IFC is often the better choice. In that case, FEM-Design helps us turn physical geometry into a clean analytical model with tools for filtering, correction, connection, and checking. So the key message is simple. The better we choose the workflow, the less time we spend fixing the model later. Sometimes the object type itself tells us which workflow to use. For example, complex physical geometry should come through IFC, not through the add-in. In FEM-Design, we should then split and simplify it to make it ready for analysis. It is also useful to agree on workflow with the other disciplines before the exchange starts. Decide what model will be sent, what should be included, what coordinates to use, what each software can handle, for example, Revit or Tekla or FEM-Design, and who corrects the what. This makes the exchange smoother and more predictable. I know this was a lot of information for today, so you may want to come back to some parts later. We record this webinar and we will publish it on our YouTube channel, so the details will remain available. If any questions come up after the webinar, please feel free to send them to me by email. And if you see practical problems or missing features in these workflows, please let us know. Your feedback is very welcome and helps us improve the Revit FEM-Design connections further. Thank you for your attention.